right, welcome. Thanks for coming to my talk. Enjoy your lunch if you are eating. Let's talk about live events. So, live events such as Olympics, major sports and esports events, even US presidential debate, they attract large audience. It's millions of concurrent users watching the event. In past, these events were typically watched on a linear TV via traditional broadcasting, so over cable or satellite. That's the TV of the old days. It's you tune in a specific moment on a specific channel to watch a specific show. And you also get a specific advertisement. Everybody kind of gets the same, or at least everybody in the same region. Nowadays, viewership is more and more transitioning to digital mediums. That's phones, laptops, tablets, gaming consoles, and especially connected TVs. All of these devices are internet-enabled, and that means more flexibility. You can tune in to your favorite streaming platform at any given moment to watch whatever you want. This shift also enabled much more flexibility for the advertisement world. So you know really well how a commercial break looks like from the viewer perspective. In this talk, I will tell you a bit more how it looks like from the EdTech perspective or EdTech world. I'm Ivan Schwarz. I'm representing DoubleVerify here at Devox. We are an international EdTech company with offices all around the world, including the beautiful city of Ghent. That's where I sit. And we have a booth here at Devox. So please do come by, say hi, learn a little bit what we do and how is it interesting for you. This is my first ever conference speaker experience. You maybe already noticed, but I would love to get some feedback from you. There is the Devox companion app. You can rate it, share some feedback, but you can also just do it the old way and grab me on the hallway and have a chat. This talk is pretty high level. I try to keep it high level, but each part of the story has much more depth. And yeah, I'm always happy to talk with fellow engineers to discuss the nitty-gritty details. Okay, so. Let's break down what we are facing here. I will start with a delivery flow for live events, and it all starts with a broadcast production center. That's a van or typically maybe a small booth, like a studio booth at the event, and they are responsible for the transition between the content stream and the advertisement. So they are ultimately in control of what we in the industry call the big red button. And if you hit that button, if they ultimately hit that button, it encodes a very specific signal into the stream. This signal is standardized, and it contains information about the duration of an ad break, and of course the start of the ad break, and a bunch of other information which is relevant, but not for this talk. So this, by nature, makes these commercial breaks unpredictable. So they typically push the button when there is a dull moment in the match. Maybe there is a problem with the playing field. Maybe there is a maintenance of the equipment. There are, periods and breaks between the periods of the play. Maybe there's an extension of the game and so forth. Once there is a stream with these markers for advertisement, they are passed to a component responsible for server-side ad insertion. This component for every single viewer connected to the stream, it makes an ad request or ad requests if there are multiple ads in the break. So every single viewer gets their own. Once it gets all these ads, it then stitches it into the content stream and makes it available to the viewer. This is quite important for you because the fact that it happens on the server side is likely the reason why your ad blocker might be struggling. Since there's no call from the client machine, it's much more efficient, much more healthy for for the resource management of your machine and the networking layer. But it it makes it much more hard for the ad blocker to detect this. So let's sum this up and let's pick up the important parts for the auto scaling and for the scalability of the system. There are major live events with millions of users, millions of viewers. They do have commercial breaks, and these breaks have actually length and timing. Commercial breaks is signalized by someone at the event pushing the big red button. And once this button is pushed, the ad tech world has just a few seconds to provide the commercial break ad content. I also have an example to make it a bit more tangible. Consider 3 million concurrent viewers, 6 ad slots in the break. Let's say DV is lucky enough to be involved in all of these ads. And let's say we get 7 seconds. That is roughly 2.5 million requests per second. This formula is a bit more complicated in the real world. Sometimes you get 6 seconds or 5 seconds. There's a jitter involved. The request per second distribution is not constant, but I think this gives you some idea about the challenge. So what are actually the challenges related to this kind of traffic pattern? First of all, you might not see this traffic pattern in your metrics. Let's say the spike duration is 4 to 7 seconds, but the metrics are usually with a 1 minute granularity. That's kind of the default what you get from most of the cloud providers or infrastructure providers. But if you have 1 minute granularity, most of that 1 minute actually captures the baseline. So your spike gets really watered down in your metrics. You can see it pretty well on the graph on the right. So on the top you have minute granularity, on the bottom you have second granularity. And you can actually see that the biggest spike on the graph on the bottom is manifesting itself just as a minor increase on the top, while the biggest spike on the top is actually a bit longer surge at the bottom. So in general, surge is less dangerous because your system has better chance to react. While this kind of bullet spike, that's the danger. The second challenge is that you might not even know you have a problem because synthetic monitoring checks, let's say uptime checks, they are typically every quarter, half minute. Considering your infrastructure is reasonably resilient and it can recover quickly, you might be actually lucky to get 1 negative data point from your synthetic monitoring. And even then, the alerting is typically set up in a way that it needs a few consecutive negative data points before you get your engineer out of the bed. These mini degradations are also under the radar because the blast radius is actually not so large. Typically, is one of your locations struggling for a few seconds. So your customers might not really even notice because it's 0.00 something of their traffic which is affected, but the one really suffering is the source of this spike. In that case, for them, that could be half of their traffic gone. In worst case scenario, you might not even see an ad. Well, no, I'm joking. They actually have fallback solutions for that, but they will lose money and they will knock on your doors for explanations. The last challenge I have here, and that's actually the title of the presentation, that auto-scaling isn't fast enough. Like I said, spike duration 4 to 7 seconds. It takes time to recognize that you are in trouble, but it takes more time to actually provision new resources. You can get 2 seconds actually of a boot time. I've seen some crazy things people are able to do, and you can go as low as maybe 5 seconds, something like that. But even 5 seconds is too late. Well, at the time your resources are up, the spike is over. Okay, so what are we going to do about this? First of all, we need a good view on the problem, on the traffic pattern. So second granularity is good, milliseconds is even better. The graphs on the right is actually, that's a snapshot from an action analysis from one of our brilliant data analysts. And with this specific service, it actually, for every incoming request, it makes a sub request. And on top, you see it, the timing is really aligned. On the bottom, and that's the unhealthy behavior, it's actually delayed. It signalizes an issue in the networking layer that's not critical here. But what is kind of the important part here is that all of the important information actually happened within 1 second. So I actually hit the x-axis because the timestamps of all the milliseconds were just unreadable. The granularity is really important. The second part of this is that a lot of important information lives outside of the application layer, and that's also what happened here. Like I said, it was actually a bottleneck in the networking layer for outgoing requests. So it's really important that you take your lifecycle or request response lifecycle and you break it down. Tracing typically is really helpful. Load testing is also very useful to kind of identify the bottlenecks, although distributed load testing is kind of I would say challenge of its own. But what we end up doing is access log based metrics. So we generate a log for every incoming request, for every outgoing request, and its typical access log contains relevant information such as status code, location, URL. But more importantly, in this case, we kind of note timestamps for every single stage of the life cycle. And this allows us to capture full networking context. It allows us to avoid any percentiles, and it's as granular as it gets. But it's not real time, so you cannot really make on-the-fly decisions based on this. So let's say we actually have a view of what's going on. What can we do about it? Well, the first thing what you might consider is actually doing nothing. We too often see engineers, let's rewrite this in Rust or other favorite high-performance language, or let's switch a cloud provider, or let's start building our own stuff in terms of bare metal. But the problem we are facing here is actually not really a trivial one. So someone better has a good reason to do this. This good reason typically involves a big, large enough bag of money, or strategic partnership, or similar incentive. But it should be indeed important problem enough for you to solve it. What you can also do, and what's typically referred as throwing money at the problem, you can just keep all your resources up for to kind of cover the worst case scenario. That's usually not cost efficient, but it can work if your single compute unit is, considering application and the surrounding infrastructure, if it's optimized well enough to make it really cheap, the large bag of money coming from the customer is indeed large enough, then it might actually work. Or at least it gives you a stopgap until you figure out something better. The second thing you can also do is try to avoid this traffic. Can you perhaps deliver your product in a different way? In our case, we actually managed to deliver part of our technology by collaborating with another partner involved in the chain as well. So we kind of removed ourselves from the chain. And I think it's really important to talk to your customer here. Like I said, this is not a trivial problem, and they are most likely aware of it because there will be other partners they work with who struggle as well. So can they perhaps, pace the traffic? Can they maybe artificially send it to multiple locations instead of maybe the nearest one? Okay, let's say we want to solve this. And I will not go here too deep into routing and balancing, but I want to touch on unicast versus anycast. So a quick refresher. For unicast, when you make your DNS lookup, you get an IP, DNS lookup for www.yourservice.com. You get an IP or set of IPs, and this IP leads to a single server. That kind of puts the decision where to route on the DNS layer. With anycast, you get the same, right? You get the DNS lookup, you get your IP or set of IPs, but in this case, this IP is advertised by the whole anycast network. So every single machine in the network is saying, I am, the same IP. And that actually moves the routing decision where to route to the much later stage, making it more flexible, so into the networking layer. So this is typically more difficult to set up, but it's typically also much more resistant and resilient in the high scale scenarios. What we quickly found out is that it's not a silver bullet, and that kind of brings me to the second bullet point here: big versus small data centers. We have hundreds of locations for our services, and the idea is be close to the customer, have as low latency as possible so we can get the ads on your machine as fast as possible, so you don't see this annoying spinner, and most importantly, you are still around when the ad arrives. We try to have a lot of machines, but if these locations are many, then it's also pretty difficult to keep them all really well equipped, to keep them all with a lot of resources. So inevitably, some of the locations are small and some of them are bigger. And then we are entering a trade-off where if you have a lot of locations and some of them are pretty small, then these locations are not really well equipped to handle high volume spikes. If you have small amount of locations, then you can make them bigger and they are well equipped to handle spikes, but your general latency will be higher. So that kind of brings me back to anycast and where it actually still struggles is that in ideal world, you would think, okay, the traffic will be routed to the nearest data center. It will kind of figure out on the fly how much it can handle, and then it will spread out the rest to the rest of the network. But with the spikes as sharp and as high as this one and as short as this one's, then we found out that even anycast framework has quite troubles to react in time. So if you then get traffic routed to your nearest data center, and that one is small, then you could find out that your anycast network is as weak as its weakest data point. As weakest location. So this is something we are working on with our cloud, with our infrastructure partner, but it's not there yet. So what we do, until it gets figured out, we actually have two anycast configurations. We have one for our standard traffic, and we try to identify traffic where there is really low chance of a live event, and we kind of split it out. And then we have traffic where we have high chances of live events, and then we actually have anycast configuration where only the biggest locations, the biggest data centers are advertising the IP. Okay, I mentioned that auto-scaling is not fast enough, so what can we actually do in terms of scaling? So the first thing every cloud provider will tell you is, well, have seasonality scaling. When there is rush hours, scale up. When there's calm hours, scale down. And that can be smarter than just keeping your resources up at all times if you know that during the calm hours you have no live events. For a globally distributed business, for a global business, this is not really an option, but perhaps for the local one it could be. I would say a bit more smarter way, or at least a bit more deterministic way, is using a calendar. If you know that you are covering a Champions League or NFL or whatever, you actually know how the season looks like. You can set up a calendar and scale up and down based on that. Or better yet, talk to your customer, let them send you the calendar. But while this is smarter, it's not really bulletproof, because this is usually a bunch of emails and Slack messages, and people make mistakes. And what can also easily happen is one of these matches gets rescheduled, and then you are in trouble. So where the industry is actually, arriving at, and that's actually pretty recent development in our industry, is something what I refer here to as adaptive scaling. So that's actually a standardized API, and like I said, parts of it got standardized just about a month ago, and parts of it are not yet standardized, but there's a bunch of proprietary solutions already available. But the idea is that the publishers of these live events, they publish these events with associated information such as, how many people is watching this, or what are the locations and so forth. And that allows entities involved in a delivery flow, such as DV, to programmatically subscribe and consume this information, and then you can actually have fast enough scaling because it scales before. All right, the last piece I want to talk about is the application itself. I'm not going to tell you how to write efficient Java code because there's enough content for it, probably on this very conference. But I want to talk a little bit in the spirit of this session about some alternative options. So, high throughput is essential when you are handling high volume. That's pretty clear, right? The faster you can serve your request, the faster you can serve the next one. But can you actually acknowledge your bottlenecks in your application and or infrastructure and kind of be conscious about it? And perhaps you can just put a queue or cache in between and just let the request wait and serve it when you have more resources. That pretty dramatically increases latency. But if your scenario permits it, then this can actually be a viable solution. And then the application layer itself plays a big role. The one thing I want to really stress is the online versus offline part. Whenever you design an application which is going to be used on a high scale, do the bare minimum. So if you can offload anything to the offline process, offload it to the offline process. This is actually how most of the data pipelines are designed nowadays. Ideally, when you consume data, you log this raw data and you return, and then that's it. If there is any processing, any transformation of this data, that should happen offline, where you have when it's cheaper and more safe. The second part of this is actually reduced service, and that's kind of contemplating what is your core business, what is your core feature, and how much of resources this core feature needs. And then what are the nice to haves and how much resources they require. What you can consider for live event or any high scale traffic is just let's do the bare minimum, and if it's nice to have, then maybe that's not so important for this type of traffic, or at least it's not worth risking an outage. You can do this consciously, and you can have separate build for this type of traffic, or at least separate code path. But you could also do this on the fly. So if your service finds out, I'm in trouble, maybe it can kind of swap into this reduced service mode, and at the very least, it can do no harm. And instead of returning 503s, you can return reduced service, or if you are in a chain of request response, and you can just proxy, for example, and do no harm. So that's more of the short circuiting. So I have some key takeaways here to recap. Well, first of all, always make sure you have a right view on the problem. Consider trade-offs and alternatives before you try to just solve it all yourself. Understand, or better, test for limits of the standard solutions, because as you could see here, standard solutions are not always well performing in non-standard situations. And then build collaborative relationships with the other stakeholders. And in this case, it's not always natural. You always feel like, okay, customer is the customer. They're always right. I need to, serve the full product at all, terms and cost. But it's not always the case. It's always a discussion. And even the biggest contributors can become collaborators if their business is threatened. And then, I have the last one about the application, which is identify the critical path for your service to deliver value. And that's all what's in store for you. Thank you for your attention, and I will stick around for questions, definitely. But otherwise, see you at the DV booth.